when I say A mod n equals R, that is equivalent to saying that when you divide A by n, you get a remainder of R, where the remainder satisfies the conditions of the division algorithm. This is equivalent to saying there exists a unique Q in the integers such that A equals Q times n plus R, with R being between 0 and n, the thing I'm dividing by, possibly equal to 0, but not equal to n. So for example, 22 mod 6, what's the remainder I get? When I divide 22 by 6, I get a remainder of 4. 22, like I said before, equals 6 times 3 plus 4 is the way the form of the division algorithm works. You should realize that if you don't satisfy the condition that R is between 0 and n, that you can certainly find other Q's and other R's. It also does, for example, equal 6 times 2 plus 10, or 6 times 1 plus 16, or 6 times -1 plus 28, or 6 times 4 plus -2. There are infinitely many ways you can write 22 as 6 times something plus something else. It's only this way that you write it, where the remainder is between 0 and R, possibly equal to 0, but not equal to n, the thing you're dividing by, which in this case is 6. Modular arithmetic can be proved to satisfy lots of really nice properties. For example, if you want to compute, say, 38 plus 61 mod 6, you can mod first to make your work a little simpler. In other words, this equals 38 mod 6 plus 61 mod 6, and then possibly you also want to mod by 6 at the end, if you don't get a number between 0 and 6, possibly equal to 0, but less than 6. 38 mod 6, what's the remainder you get when you divide 38 by 6? It's 2. 61 mod 6, what's the remainder when you divide 61 by 6? It's 1. So you get 3 mod 6. The remainder when you divide 3 by 6 is 3. 3 equals 6 times 0 plus 3. And that remainder is between 0 and 6, possibly equal to 0, but not equal to 6. If I had done, to make it a little bit more interesting, if I had made the 61, say, a 65, then I would have had a 65 here, and a 5 there, and a 7 there, and then finally a 1, just to make it a bit more interesting. So I really do need to mod at the end in an interesting way. Let's consider that example. The alternative way, the way you do it, if you didn't know this property, you'd do 38 plus 65 first, and you get what, 103 mod 6. What's the remainder when you divide 103 by 6? 6 goes evenly into, for example, 90 and 96 and 102. Yeah, the remainder is 1, just like we got over there. Now, you might say writing all this is more work than just doing that. And that certainly seems to be true if you bother to write all this. But usually we don't bother to write all this. Usually we jump from 38 plus 65 mod 6 right away to 2 plus 5 mod 6. And we see that that's going to be 1. We don't typically bother writing this intermediate step. But that's technically what we're using. It works with multiplication as well. And with multiplication, it's actually a lot more useful, you might say, because while you can do 38 plus 65 pretty easily in your head, it's not so easy to do 38 times 65 in your head. 38 times 65 mod 6. I mean, yes, I hope you could still do it by hand without a calculator if you needed to. But if we are modding by 6 here, it's a lot quicker to mod first. 38 mod 6 is 2. 65 mod 6 is 5. So this is going to be 2 times 5 mod 6. 2 times 5 is, of course, 10. And 10 mod 6 is 4. If you didn't know that you could do this property, you'd have to literally do the multiplication of 38 times 65, either by hand or with a calculator. 38 times 65 is 2,470. When I divide 2,470 by 6, I get a quotient of 411, a decimal part of 0.6 repeating, which is 2/3, or 4/6. The remainder would be 4. This is 4, it matches. Okay, so modular arithmetic is nice for calculations. It's got some applications, as the author gets into, to the ISBN codes, for example, and check digits. It's a lot more important when people actually had to type in ISB numbers, which we did used to have to do like 30 years ago in a cash register instead of just scanning them with a laser. Maybe it was 40 years ago. But it's still an important thing to learn about, I think, as an application of modular arithmetic. It's got other applications as well, including to cryptography, secret codes that keep your internet transactions secure. It's based on modular arithmetic and some other things.